So yeah. So we're done with linear regression. We did the ordinary least square. We did ridge regression and lasso, which are two types of regularizations, okay, which allow to prevent overfitting. And again, these techniques, you can apply them to any optimization problem you want, any learning algorithm you want. If you want to constrain your solution, you can add a L1 or L2 penalty completely generically, okay? And this is what really people do for complicated applications. And they are more advanced thing, but 99% of people use these two regularizations for any kind of problems, okay? Okay, so I want to just do some numerics, additional numerics on that. So where are all my things? Okay, so I need to share. Okay, it's a mess with 3 computers. I'm lost. Okay, let's see. I want to do share. Okay, like this. Okay, do you see my screen? Yes. Okay, great. Okay, here is a typical computer of a researcher. Okay. Okay. Here. All right. So I need to make that small. I want to reduce that. Ah, you don't see it. Okay, that's fine. So let's do a few more experiments with linear regression, and then we'll discuss today gradient descent and stochastic gradient descent, which are essentially the number one by far optimization algorithms. Okay, so in the sense that we discussed linear regression, and in the very special case of least square and ridge regression, you can write down the solution explicitly. And by solution, I mean the minimizer of the cost, or the penalized cost in the case of ridge regression. Okay, because the problem is linear. Linear algebra directly gives you the answer. Okay, in terms of the design matrix and the labels. But in general, life is not as easy. Okay, so even if your cost function is convex, it's not necessarily the case that you can write down the solution explicitly. Okay, and one case where we already encountered this problem is Lasso with L1 penalization. Even if the overall cost is convex, you cannot write down the solution explicitly. Except in the very special case where the design matrix, the X, is orthogonal, okay? But of course, this is not the case in general, okay? And so we'll need to discuss how to find minima of functions, of complicated functions like this, okay? And this is the purpose of today. But before that, let's do some more experiments with linear regression. So I hope that you had a look at this notebook 4, which for me is the nicest application that will, one of the nicest in this course, I think. I find it very, very cool. So let's see. The idea is that we want to use linear regression to solve statistical mechanics problems in the sense of learning an Ising model. Okay, so I will assume that most of you, if not everyone, knows what is the Ising model. Is that a correct assumption? So you, I know, but for those that are online, I see Simone, the only one that activated the camera, moving his head like this. So.
Not so much.
Not so much. What is your background?
Physics and geophysics.
Okay, I see. Yes.
For CMSP students, we studied this before.
Okay. So yeah, unfortunately, I won't have the time to do a whole introduction to the Ising model, but to make it short, it's a spin model. So it's a system of interacting spins, which are just the physics names for binary variables, which take plus and -1 values. And this system is associated an energy, okay, an energy function, and this the state of the system is described by this vector S. We'll consider in particular the simplest Ising model of them all, which is the one-dimensional Ising model. So this one-dimensional model is described by binary variables, which is a vector of size L in this case, which is the number of spins. And the probability distribution describing this random system has the form of what we call Gibbs-Boltzmann distribution, which is it written explicitly here? Yes, it's written explicitly. It is this exponential form where beta represents an inverse temperature, okay? And H is the energy, or what we call the Hamiltonian also, and it depends on the configuration in which the system is, which is this vector S, okay? So for those who do not know these things, I advise you to have a look at this exercise, which is rather simple, but very interesting. So we want to understand a bit this system, but from a machine learning perspective. So we want, essentially, we'll forget completely the statistical mechanics that is behind, and we'll consider a purely machine learning approach. Okay, so we're not physicists anymore, we're data scientists. And what will be given to us is a data set. And what is the data set? It will come in the form of random configurations of spins. Okay, so one configuration means a vector of length L of binary variables. Okay, that takes plus and -1 values. And the associated label will be what? Will be the energy of this configuration, which is computed according to this Hamiltonian here, to this function here. And J here is the so-called coupling strength, and we take it constant, okay, and positive, which means that it's a ferromagnetic model, okay. So this energy, okay, we see that so for those who are not totally familiar with that, we have an exponential minus the energy, okay, which means that the configurations with a lower energy tends to be favored. They have a higher probability, okay? So if we look at the energy, a low energy, if we consider J to be positive, which means a ferromagnetic model, a low energy corresponds to configurations where neighbor spins, so let's say Sj and Sj plus 1, you can think of these spins on a chain, on a closed chain, a ring. Neighbor spins, they want to align with each other. So, okay, this lower the energy. Okay, each time they align, you gain a unit of energy scaled by J. So you gain a minus J of energy, or you lose J units of energy. While when they anti-align, you gain a plus J of energy, okay? So, all right. So let me say that I give you a lot of configurations and their associated energies. How many configurations there are in total? Okay, we have a binary systems. Each variable takes 2 possible values. So there are 2 to the power L possible configurations. I will not give all of them to you. Okay, I will, because this is a huge number, even if L is small. Okay, this is exponential is in L, and that's all the point is statistical mechanics. Exponentials grow fast. So I will give you a subset of these configurations and the associated energies. Okay. So suppose that I give you this set. Okay. So the data comes in the form of configurations and associated energies. So the labels are this H of SI. It's a scalar. It's just a number. Okay. While these are large dimensional vectors. Okay. L dimensional vectors, each SI. And I give you N of these data points. Okay. Your task will be to learn the Hamiltonian. Okay. To reconstruct from these configurations the energy function. Okay. So in physics, and actually also in signal processing, but in physics, this is called an inverse problems. Okay, you are trying to reconstruct the system, the energy function from configurations. Okay, while the direct problem usually in statistical mechanics is that you are given the energy function. Okay, you know what is the form of the energy. And then you want to deduce from that things like compute the magnetization, like understand where are the phase transitions and so on and so forth. Okay, so this is the direct problem. You know the energy, this defines the system. And then from there, you want to predict things about the system. Okay, here we are solving an inverse problem. You don't know the system, you don't know the energy function. I give you samples generated according to this system, okay, random configurations, the associated energies, and you want to infer what is the system. So it's an inverse problem. Okay. Okay. All right. So here is a small piece of code. Again, I will not spend too much time on the details, but essentially here I'm defining the size of the system, the number of spins on the ring. Here will be the number of training samples, the number of test samples, and N is the total number of samples. Okay. This line here is just generating random configurations. Okay, so it takes values in -1, 1, and this means in the discrete set -1 and 1. Okay, it's not the continuous set of all the real numbers between -1 and 1, and it will generate N such configurations of size L. Okay, and here is the Hamiltonian of the problem. Okay, which will you see it's doing a sum here where it's summing over for a given configuration I. It is for a given configuration, it is summing the position, the state of the spin at position L-1 times the one at position L. Okay, and it's looping over the ring like this. So it's looking at all the neighbor pairs doing the product, and it's summing over that. And the last one is just separated because here, this means that you have a closed boundary condition. You are looking at the very last spin with the first one. Okay, so you are closing the ring. All right, so, and here I'm generating these energies. So for each states that were generated here, I'm outputting the labels, which are these energies. Okay, so now this is hidden to us. Okay, this is what physicists obtain in the lab, and now we close the eyes. We don't know this function. We are just given this data set. Okay, and our task will be to learn this function. But let's say that we don't have very strong a priori knowledge about what this function should be. So we'll assume a more generic form for this function, okay? Just to be on the safe side, to make sure that we can capture, we have some knowledge, we know that this comes from some statistical model, okay? So we'll assume a form of an energy, but which will be more generic, okay, than what we are actually trying to learn, which means what in the vocabulary of machine learning, which means that our hypothesis class is bigger, okay, it contains the actual model that we're trying to learn, okay? And in this case, our hypothesis class, if you want, will come in the form of all functions that are Ising models also, but two-dimensional Ising models. Okay? And of course, a one-dimensional Ising model is a special case. Okay? The one-dimensional Ising model is the same energy, but where you would have the J case here, this interaction strength would be 0 when J is different than K, and it will be constant otherwise and equal to J. This is what we are trying to learn. Okay. All right. So this form of functions with a two-dimensional Ising model with not with local interactions like this, like a not unhomogeneous Ising model, pairwise Ising model is not very restricted. It's actually an extremely generic class of functions. You can capture extremely complicated model with this type of energies. Okay, that's why as physicists we can spend careers on studying the Ising models, because you can map infinitely many complicated functions and models onto that. Okay, so this is not a strong restriction. Actually, it's a very large hypothesis class. Okay, so we need to cast the learning problem into a linear form because we want to do linear regression. Okay, so what we'll do is that the first thing we'll do is that we'll represent, you see here you have actually this, if you fix a configuration, which is the case here, this is a matrix indexed by JK. Okay, the first thing we'll do is that we'll represent this matrix of configurations as a vector. We'll vectorize this matrix. So if you want, you can think of JK as a single index now. Okay, and an entry of this vector whose indices are all the pairs JK is a product like this. Okay, so what does it mean? I'm just saying that you can represent this double sum, okay, into a single sum over what we call a multi-index, okay, of this form. Now it's a linear problem, and this matrix J, this vector J is also a vectorized form of this big matrix JJK. You can think of it like this. You take a matrix and you take the first column, then you take the second column of the matrix that you put after, then the third column of the matrix that you put after, and so on and so forth. You are just vectorizing a matrix. You can do that all the time. So we just represented this Hamiltonian into a linear form. Okay. And our task is to learn, okay, this coefficient J. Okay. So you see what I called Xi now is the vectorized form of this product. So a component of Xi is one product like this. Okay. And the indices, what I call a multi-index, is a pair of indices of the original matrix. Okay. Is it clear? Okay. So we just rewrote our energy function in this linear form. And now P goes from 1 to L squared, which is the total number of elements in this in the original matrix, which is now a vector. Okay. All right. So you see that each time I give you a configuration, okay, you can now define this X, okay, and this gives you a sample, okay. So here, this is what I'm doing. I'm just reshaping the original matrix of states where I'm doing this operation that I said. So now I'm creating this vector X from all the possible products. So for a given configuration, I'm doing all the possible products. Okay, I have P squared products, and I get this vector XP of size L squared. Okay. And this defines my data. It's this vectorized configurations and the associated energies. Okay. If it goes a bit fast, you just grasp the idea and then think again about it at home here in Italy. So now I'm dividing the data into training and test data as usual. Okay. And I will, just to make things a bit more interesting, I will add a bit of noise in the training labels. Okay. So here is a Gaussian noise. Okay. So here are the training labels, and I'm adding a bit of noise, and similarly in the test labels. Okay. All right. So now I will apply my three forms of linear regression that we discussed: ordinary least square, ridge regression, and lasso, on this linear task of learning a two-dimensional Ising model. Okay. So also this should give you a hint of how linear regression is actually generic. You know, even if your data comes in the form of a high-dimensional tensor, okay, which is actually generically the form in which data comes from. Okay, you have multiple dimensions. You can still do linear regression by vectorizing your tensor. Okay. I'm not saying that it's always a good idea, but you can. Sometimes it's not a good idea because, you know, when you vectorize a matrix, for example, you may lose like correlations between neighbors. So for example, if you want to process an image with an algorithm, okay, maybe you can do a linear regression, you can vectorize your image, but actually the pixels that are neighbors in one dimension, let's say these dimensions or this dimension, so there is also information in the correlations along the second dimension that you lose when you vectorize things, possibly. But you can, okay? But if you want to exploit the two-dimensional structure, you can use other type of algorithms, like what we call convolutional neural networks and these kind of things that are made to exploit that, okay? But still, linear regression is almost always applicable, okay? So here I'm setting my least square, ridge, and lasso procedures. Okay, these are objects. I'm just initializing things. And here I'm I'm fitting my least square model, my ordinary least square. Okay. And here I will loop over what? Over the value of the regularization in ridge and lasso. Okay. So I will do cross-validation. I'm scanning over a large range of values for the regularization. For each of these regularization strengths, I will compare the training error and the test error. Okay, and I should select the regularization that leads to the lowest test error. Okay. All right. So here each time I'm retraining the same least square. This is redundant because it does not depend on the regularization strength, which is this lambda, but it's just because it's easier, and then to plot things, it goes faster, but it doesn't change it. So here, each time I'm setting my ridge regression, I'm creating the object, I'm fitting the training data, and here I'm just storing the weights that I'm reconstructing, the weights of this J matrix or this J vector that I'm reconstructing. Okay, and I'm storing the error I make on the training data. Okay, what is called the score here. So it's not a mean square error; it's another error metric. Okay, we will see, but it's like a mean square error. Actually, it's a score. You want this to be high. But it's a measure of performance. And I'm looking at the score and the test set. Okay, and I do the same for lasso. And then I'm just plotting what I reconstructed. Okay, so I reconstructed a L squared dimensional vector. And then I'm just reshaping this vector into a matrix. Okay. I'm just here reshaping the vector that I reconstructed by lasso, ridge, or least square again in a matrix form, and I'm plotting the matrix to see what we got. Okay, so let's do this experiment. Okay, I run it. And what do we observe? We observe this. Okay, so let's see. Let's zoom out a bit to have. Okay, so on the left, you have the reconstruction of this matrix from how many samples? We said from 500 training samples and associated energies. Okay. In the middle, you have a ridge regression for different values of the penalization, the regularization strength, and the reconstruction from the lasso with the same penalization. Okay. And as we go down, we are changing the penalization for lasso and ridge. While on the left, nothing changed. It's always the same least square estimator. What do you expect? Which one will be the best? And you have an argument for that. So here in blue, so dark means -1, red is +1. So it's the value of the interactions that you reconstruct, okay? And white means 0. So what should we reconstruct in the best if we were reconstructing the matrix perfectly? How should look this matrix? Sorry? Say it again. Yeah, but what is the picture that we would like to reconstruct? This matrix, like the original matrix of the original Ising model. I show you again the form of the Hamiltonian. It's here, okay? And what we are reconstruct, so you see, we have just interactions between neighbors along one dimension, okay? And we are trying to reconstruct a model of this form. So what I'm asking essentially is this matrix JJK here that we're reconstructing, what value should it take to be the original Hamiltonian? And I already gave the answer before. Not diagonal, because you see, almost diagonal. Because you see the interaction is between S, J, and J plus 1. So you should have a line on the upper diagonal. Okay? On the diagonal means that you would have sum of J of Sj squared, which is not what we have. To have a coupling, you need elements on the above diagonal. Yeah. It should be 0 on the diagonal. It should be 0 everywhere except for the first upper diagonal. Okay. So now that we know what we're looking for, what we expect, which method will be the best and why? We already see the end. Which method will be the best? It will be Lasso. And why? Why is that so? Because Lasso, what is the property of Lasso? Why do we like Lasso compared to Ridge? What is really the main point of Lasso? Lasso has one main advantage with respect to Ridge that we discussed at length. I think what you should keep in mind always is the geometric interpretation of Lasso versus Ridge. You remember with Ridge, there are in the cost function of Ridge regression, there are two terms which are both quadratic in the arguments that you are trying to optimize over. And when there is a competition between two quadratic terms, it's like you are trying to match, to find the intersections of balls or ellipsoids. And so ellipsoids are smooth, okay? They don't have corners. So you are restricting the norm of the vector, and that's it. While with Lasso, the L1 penalty, you remember in the constrained optimization version of the Lasso, you have the quadratic cost, and you are optimizing a set of vectors which have a L1 norm which is less than something, and the L1 norm defines a sharp region in RP with corners. And when you try to intersect an ellipsoid, which is a smooth object, with a diamond, which is defined by this L1 restriction, this penalty on L1, with high probability, these two shapes will intersect at corners of the diamond. Therefore, Lasso is enforcing many components to be strictly equal to 0. So it's good for interpretability, okay? But it's not only good for interpretability, it's also what you should use if you really expect some model to have many zeros. And here, this is what we expect, okay? This Ising model, we want to have zeros everywhere on this matrix except on the upper diagonal. And indeed, we see that as we increase the regularization, I'm going down. Each time you can see the test error, okay, and the value of the regularization. It's not an error here. Again, it's a performance. The higher, the better. The maximum being 1. Okay. So first, you see that even the ordinary least square, so the test error performance is not so bad, and the training performance is 1. So again, here we are overfitting. The training performance is the best. Okay. And this is actually usually not such a good sign. Okay, you are fitting noise here, and indeed we see that the matrix that we reconstruct is noisy. There are no components equal to 0, and we see that may look strange that we see that we reconstruct like the upper and lower diagonal, not just an upper diagonal. We'll try to understand why. While with Lasso, that you see if the regularization strength is small, it's also noisy, but as we increase the regularization strength, we see that it's less and less noisy, while with Ridge, it seems that nothing really changed and the test performance is comparable to ordinary least square. But you see there is a kind of sweet spot here for a regularization strength of 0.1, where we almost perfectly reconstructed the actual model. Okay, you see that there are minus ones just on the diagonal. Remember, in the linear regression problem that we were trying to solve, the model was j times x. So we are trying to, and the original model, we have a minus j with j equal 1. So we're trying to reconstruct minus ones on the upper diagonal. And this is what we see here. We have a minus 1 value, blue, on the upper diagonal. Okay. But you have to realize here that we have very few samples, like 500 is not so big compared to the total number of possible configurations, which is 2 to the power 40 in this case. 2 to the power 40 is you have no idea how huge it is. It's a really huge number. So we have an vanishingly small subset of configurations and associated energy, and Lasso is able to almost perfectly reconstruct the model. Okay, so it's very powerful. And you see the test error, the test performance is 0.95, which is almost the same as the training error. So here you are in a setting where you have almost no overfitting. Okay. So let's try to understand why Ridge is and ordinary least square are reconstructing something both above and below the diagonal, while Lasso is not. Because you see, the original model here, which is there, okay, this energy function that we're trying to reconstruct, it has an invariance, what we call a gauge symmetry in physics, which is what? Which is that you would obtain the same energy if you were divided j by 2 and summing each time over the interactions with your next neighbor and the previous ones. You are just summing 2 times half a contribution, while here we are summing 1 time each contribution. You see, I could, in the sum, I could have j minus j over 2, sum of sj of sj times sj plus 1 plus sj times sj minus 1. Okay, I would slide along the chain like this, and each time sum half a contribution, but 2 times. Because okay, so this is an invariance. It gives the same energy. Okay, it's called a gauge invariance. But you see that here, Ridge is actually reconstructing kind of a correct model in the sense that the energies associated to such, let's say on the off diagonal, let's put them to 0. If you were reconstructing really the upper and lower diagonal, it would be correct in the sense that it would fit perfectly the training data, and you could predict the energies for the future, okay, because it's the same energy function. But Lasso is breaking this symmetry and finding the correct model. Why? Because Lasso is explicitly looking for the solution with the least number of non-zero coefficients. So you have two equivalent models, one where you have 2 times more non-zero coefficients in the Hamiltonian and the correct one. So Lasso will select this one because it has less non-zero entries in the vector J. Is it clear? So Lasso breaks this invariance and refines the correct one. You cannot. If you don't know the model, then we would have no reason to, which is not true, because here you see that the test performance of this one is much better, because you see that Ridge is still extremely noisy on the off diagonals, because you see Lasso is really enforcing this small component. It thresholds them to 0. Okay, so that's why at the end we get a much better test performance. Okay, because all this noise here, this background noise, it sets it to 0. Here? So let's look at the curves actually. So you see, if you increase too much the Lasso penalty, at some point you just reconstruct zeros, of course. Okay. With the Ridge also, if the penalty is really strong. So here I'm plotting the different errors, okay, as a function of the penalization strength. So least square is in blue and it doesn't change, of course, it does not depend on this penalization. And we see that we have a gap between training and test performance. So we are overfitting, okay, which is expected. While you see that with Ridge, so the red, it essentially follows exactly the same curves as least square, but at some point you are over regularizing, okay, you are setting essentially all components to 0, and so you are completely losing the performance, okay, the test performance, which is in dashed, red dashed, decrease and get until you get 0, okay. Instead, Lasso, the behavior is much more interesting. The training performance as the two other ones is perfect when you have a small regularization, you are overfitting. But you see that there is a sweet spot. You have the training performance that starts to decrease, but at the same time, the test performance increases strongly. And here you have a sweet spot where you have no overfitting. The two values are the same. Okay, and this is the value you should select. Here you reconstructed your model. And then if you over penalize, suddenly the performance decrease. So you see, you really need cross-validation to carefully select the parameters, because you see these methods are very sensitive to that. Huh? And you have a priori no way to select one parameter if you don't do cross-validation like this, okay? All right, so you have additional things that I coded that are not in the previous, in the ones that you find on internet. So if you are curious, you can try to understand the rest, but I'm done now. And I'm again 3 times slower than expected, but that's life. Okay, so now let's discuss a bit gradient descent. So this is a new chapter, okay. You want what, sorry? Maybe let's just take 2 minutes if it's okay, like 3 minutes if it's okay for those online. So I will just go drink a glass of water and okay. Like I will pause the recording. What do you? Okay, so let's start again. So I want to discuss like stochastic gradient descent algorithms. So this will not be complicated. There is it's probably what is nice with this class of algorithms is that it's by far the simplest algorithm you can think of. Okay, that's the most stupid algorithm you can think to implement for optimizing complicated things. And at the same time, that's by far the most used and efficient. Okay, and people are doing their whole career on understanding why is that so, why such a stupid algorithm is so powerful. Okay, and it's far from obvious. Okay, and I will not discuss that. I will just explain you what is the algorithm, and will not discuss that because I don't know. I am not working in this field. But okay. Let me just like to open the notes to follow up, let's say at least approximately the notes, so that when you come back to that, you're so yeah. So now we're gonna discuss the chapter 4 of the notes essentially. So we come a bit back in the notes, but this was not useful for linear regression and all that. Okay, the implementation, how the cost function is optimized in linear regression and what we run until now in our codes was not using this algorithm. Okay, but for other type of codes, this is what you need. Okay, so again, the type of problems that we want to solve are in this form. Okay. The optimization that allows us to learn to obtain parameters are in this form. Okay, it's a certain cost of some training data. I'm not writing train everywhere, but this is it. And the test, sorry, and the training labels. Okay, am I recording? Yes. Okay, and often, not to say always, this cost can be decomposed as a sum, okay, over the samples. Okay. Sorry, and here, wait, what did I write? This is, sorry, this is, I'm a bit tired. This is the Y and our estimate of the labels according to our model. Okay, this is our model that I wrote like this also. And the Y theta of X is our prediction according to this model. Okay, and we're looking for the parameters that minimize the cost. So usually the square difference or some notion of error between the labels in our data and our predictions. Okay, and this usually comes in the form of a sum like this. Okay. All right. So what is the most stupid think you could do to try to find the minimum of this function? Like an iterative way to find the minimum of an arbitrary function that depends, okay? This, I see it as a, here I wrote explicitly its dependence in the labels and the data and all that, but now, this is the notation I will use, we should see all that really as a function of the parameters themselves. Okay, the data is fixed. Okay, what we are trying to optimize over is these parameters theta. Okay, so I'm trying to find the minimum of this function, of this cost, seen as a function of theta of the parameters. Okay, so what can you do to minimize this function? It's a C, it's not a phi. Huh? Sorry? Say it again. Yes, so, okay, what she says is taking the derivative, so setting the gradient to 0, okay? Which means what? Which means finding a point where the gradient is 0, okay? Okay, and how, if you start from, imagine that you have a complicated landscape like this, which is defined by this function, okay? The coordinates are defining, so one point in this high dimensional space represents a value of this parameter. So we are living in RP, okay? We are in the p dimensional reals, okay? And one point in this space means one coordinate. One coordinate means one value of this vector, okay? So you can see this as a kind of particle moving in a high dimensional space, okay? And we're looking for a minimum or the minimum, hopefully, in this complicated landscape, which is defined by this cost. Okay, this defines the landscape. Okay. So, for example, if you move around in the mountains, you could define the cost as the height at which you are. Okay. The minimum would mean that you are in the deepest point of the deepest valley. Okay, so let's say you are in the mountains like this. So in this case, your coordinate is two-dimensional. Okay, you can move along x and y, and your height is the cost. You are not moving along 3 dimensions in the sense that you are just making decisions in going in that direction or that direction, and the height is the cost. Okay. So you have this valley. What would you do, you locally, if you just look around and you want to find the deepest valley? What is the decision you would take? Speak a bit more loud. Uh-huh. Uh-huh. But so, okay, so yeah, you can do that. So you can evaluate the height at another point, okay? And if the height is larger in this other point, you will not go there. If it's lower, you will go there, okay? But which are the natural points to compare with? Because let's say you are really in the mountains, you cannot evaluate the height super far like this. Let's say you are in the fog, you just see locally around you. Yeah, you just look at the points around you locally, and you will just go in the direction that goes down. Okay, so you follow the gradient, or actually you go in the inverse direction of the gradient. Okay, and this is gradient descent. That's all. Okay, so to find the minimum of a complicated cost function like this, gradient descent is the following update rule. Okay, so you start from an initial guess. Okay, let's say a theta at t equals 0. Okay, again, this lives in RP. And what you will do is that, so it's usually written in 2 steps. you will evaluate a vector that is called VT, which is eta times the gradient with respect to theta of the cost, evaluated at your actual position. Okay, so I will put for t equal 1, 2 until t max. Okay, you have a loop. And then so this is called like a velocity in a sense, and you will move in the inverse direction of this velocity. I know it's a bit weird, this convention, but this is just a convention. Okay, if you prefer to think of this vector really as a velocity, which means where you will go, you just change the name of VT for minus VT. Okay, this is just a convention. Okay, so this first step here is the evaluation of the gradient. Okay, you evaluate the gradient of the cost at the position you are at time t. Okay, you evaluate the gradient. And this quantity here, this eta, is very important. It's called the learning rate. Okay. This learning rate essentially tells you by defines the scale of the increment by which you will follow the gradient. Okay. So you see that if eta is 0, the new value at time t plus 1 of the parameters is unchanged. While if theta is large, you will go, so there is a minus here, which means that you will go in the inverse direction, the opposite direction of the gradient by a large increment. You are doing bigger steps when the learning rate is large. Okay? Is it clear what is a gradient, just in case? What means this symbol here? Okay, I will write it once explicitly just in case. So the gradient with respect to theta of c at theta t, or let me just put theta or theta t. Okay, is the vector of derivatives. Okay, so the gradient, it takes a function who is real valued and which takes as input a vector, and the gradient outputs a vector composed of the derivatives, the partial derivative with respect to theta 1 of this cost evaluated in theta t, theta 2 evaluated in theta t. Okay. Is the vector of partial derivatives. Okay. All right. So is this rule clear? What is actually going on with this rule? You are just following the steepest descent. So this gradient descent algorithm is also called steepest descent. Okay. You are looking locally around you. You look where the gradient is the stronger, and you follow it by a step controlled by this learning rate. Okay. So this is a purely local algorithm. It just looks at what is going on around your estimate at time t. Okay. Okay. What can be a problem with this algorithm? So okay, here indeed there is something important. There is an initial guess. Okay. So Okay, one question. Is this a deterministic or stochastic algorithm? This is what? It's a deterministic algorithm, okay? For a given initial condition, if you run it 2 times from the same initial condition, it will read the same final point. So if you reach a local minimum and if the learning rate is small enough, you will stay there. You will not move anymore, okay? So by the way, here you have a for loop over the time, but you can have also you can also replace that. I mean, you should have a condition here, a condition something like if I don't know, for example, the absolute value between theta plus 1 minus t is less than a certain epsilon, then you stop. It means you converge. Okay. It's a stopping criterion. Okay. So it's a deterministic algorithm in the sense that indeed you will reach always the same point from the same initial condition. Okay. But this, now imagine this in a very high dimensional. It's hard to imagine high dimensions, but you should start to try, because as statistical physicists, this is more than important to think in high dimensions. If you try to picture a high dimensional landscape and this trajectory in this landscape, there are 2 issues here. One is that this algorithm is very sensitive to the initial guess. If your initial guess is bad, if you have a very rough landscape with many minima all around, okay, you will converge to the closest local minimum, and that's it. You're stuck. You have no guarantee to find the global minimum, of course. Okay, you have a guarantee to find a local minimum if the learning rate is small enough, but that's it. Okay, so imagine even in 1 dimension, if you have a cost function like this, okay, depending on where you start, okay, maybe you start from here, you will find this global this local minimum. If you start from here, you will get stuck here. Okay, if you start from here, you will get stuck here. So you see that even in 1 dimension, the problem is non-trivial. So in higher dimension, it's even worse. Okay. Okay, but that's life. This is an algorithm. Should I discuss this? Maybe not. Yes or no? Okay, I will not write equation. Let me just show this picture with the different scenarios. Okay, here is a very simple example. It's just a quadratic function of theta. Okay. And here, so the local minimum is there. Okay. The local and global, there is a unique minimum. It's a convex function. And this parabola represents the energy or the cost. Okay, here it's an energy, it's the same. So let's say you start each time from the same initialization here. There are different scenarios. This is just to emphasize how important is it to choose correctly the learning rate. And it can be a difficult task to choose it correctly. If the learning rate is very small, what will typically happen? You will do small steps. Okay, so each time you will follow the gradient, and because you do small step, the gradient is a very good approximation of where you will end up, because locally everything is linear. Okay, and when you compute the gradient, you compute the best linear approximation of the landscape. So you are almost, when the learning rate is small, you are really almost following perfectly the curve that you are moving in the landscape. Okay, you are stuck to the floor and you very slowly or adiabatically, if you want, moving along this landscape. Okay, which is good in the sense that it prevents numerical oscillations. Okay, that might happen if you have a too large learning rate. We'll see. But the problem is that it becomes very slow. Okay, so you have a computational cost for that. If you are precisely at the optimal learning rate, okay, there is a way to understand that there is such a value, at least locally, and I advise you to have a look here. I will not do it. But essentially, to find the optimal rate, what you should be able to estimate is the local curvature of the landscape, which is related to the Hessian, to the second derivative. So if you were able to compute the second derivative of your function, you get an information about what is the curvature. Okay, this is what contains the Hessian. Okay, here the Hessian is just the second derivative. It's a one-dimensional function. And if you have access to this second order information, to this Hessian, you are able to select the optimal learning rate. And then, therefore, you can reach the minimum in one step. Okay. Instead, if you have a learning rate which is higher than this optimal value, you have oscillations. Okay, you will never converge because you are doing two big steps. And so you are overshooting the minimum. You are always going too far from it. Okay, and so you have oscillations. Okay. So you see there is a trade-off between speed, so low learning, high learning rate, and numerical oscillations. If you have too high, it starts to give you nothing. Okay, because the gradient is not anymore a good approximation of the landscape around you. Right? If you want to, yes. No, you will not converge. You will not converge. You will completely diverge, actually, and we will see that numerically. Okay, I think it's nice if you have a look at what is called the Newton method, which is here. Okay, which is essentially which is gradient descent that we discuss, but you are also including the second order information. So you are actually computing the Hessian of the function, which allows you to adaptively, the algorithm finds itself what is the optimal learning rate. And also the learning rate becomes a function of the different dimensions. It may be different along each dimension. And this information is contained in the Hessian. Okay, so this is called Newton method. Have a look. It's 3 lines. Okay. But why is that not used? Why people actually do not use the Newton method if I am right now telling you that the Newton method is a way to automatically find the optimal learning rate and therefore to find the closest local minimum in just one step? The reason is that computing the Hessian, this second order derivative, is super costly. Okay, so Hessian is a n by n matrix. We're talking about sorry, here it's a p by p matrix. P is large. Okay, the number of parameters that we are trying to infer. So this type of computations are very expensive. And additionally, in the Newton method, which is there, after having computed the Hessian, you need to inverse it, which scales as the dimension of the matrix to the cube. So that is too costly in high dimensional applications. There is no way to do that. Okay, but I think it's interesting for you to still understand why is that the proper method. Okay. All right, but this is not what people are doing. Okay, this is Newton. Okay, we already discussed that, but let's mention one last time the problems with gradient descent. Gradient descent, the main drawback is that you have only a guarantee to find a local minimum. Okay, if the function has many minima everywhere, which is the case in the applications we have in mind, you have no guarantee to find the global one, and you will in most of the case not. You will find a local one. Okay. I didn't discuss that, but this is the case. Gradients, even just computing the gradient. Okay, so we forget the Hessian, which gives information about the local curvature, which is a very fine information about the local landscape. Even computing the gradient in high dimension is a very costly operation. Okay, because you see, sorry. Okay. The gradient is here. Okay, so we have P partial derivatives, but this cost function here, what is it? It's here. This cost function is itself a sum of n contributions, where n is the number of samples and it's large. So you see that computing this gradient scales as P times n, and P and n are both large. So it's a huge number of operations that you need to do numerically. Okay, so not even talking about the Hessian, just computing this gradient is super costly. So in most applications you cannot. Okay, for each of the terms in this sum here, you need to compute P numerical partial derivatives. Okay, so that's problematic, right? So we need to find a way out. Okay, let's continue the drawbacks. Gradient descent is sensitive to initial conditions. Okay, like we said, it's a deterministic algorithm. Given an initial condition, you will always reach the same minimum. Okay, and so therefore, your performance is highly dependent on how you choose the initial condition. But in most cases, you have no clue on how to choose it. Okay, so what you can think of is just trying many of them. But trying maybe 1,000 is nothing compared to the volume of the space of a p-dimensional space. Okay, the volume of a p-dimensional space scales as exponential p. It's an exponentially growing fast space. Okay, so even if you try 10 billion, you will have explored a very tiny fraction of all the possible configurations. Okay, so this is not something you can do. Okay. So in some way, we need to solve all these problems at once. And what people did to solve all these problems at once is to introduce what is called stochastic gradient descent. So we'll try to follow the notations here. Okay. So what is stochastic gradient descent? What people call SGD. So at the same time, we don't want to be anymore so sensitive to the initial condition, which means like introducing some notion of stochasticity, okay, some noise, which means that even from twice the same initial condition, 2 runs, if you run twice your algorithm from the same initial condition, we want that it converges to different things. So there is some stochasticity, okay, to avoid to be stuck in some local minima, okay? Because you see that with stochastic gradient descent, even if you are stuck, with gradient descent, even if you are stuck on a local minimum like this with a very small barrier that prevents you to find a much better one here, you will remain there. But you see, if you could introduce a bit of stochasticity, a bit of temperature, if you want to be able to jump around this barrier, maybe you could find that one. And maybe if you have enough stochasticity, you will be able to climb all these walls and actually get stuck here, the global minimum. Okay, so in physics terms, we want to introduce some temperature, okay, some notion of stochasticity, some noise, okay? Okay, and at the same time, we want the algorithm to be less computationally expensive, okay? We are not able to compute the gradients over all the samples. There are just too many, so we need to face that. And SGD is something very simple. The idea is very simple. It's just to say that instead of computing in gradient descent the gradient with respect to the whole cost function, which again is in this form, this is our model prediction. Okay, what we'll do is define what we call mini batches. Mini batches means that we'll select just few samples randomly, okay, and compute the gradient just on these few samples. So not on the whole cost function, but on a subset of the terms that appear in this sum. A small subset, okay? Maybe in your training data, you have 100,000 samples. What you will do instead is that you will take your 100,000 samples and divide that into small chunks of 10 samples. And each time you will compute a gradient, you will just select one of the mini batch, compute the gradient on it, and follow the rule of gradient descent. Follow the gradient along this direction. So why is that noisy or stochastic? Because the stochasticity here is the random choice of these mini batches. Okay, these mini batches are drawn randomly. So if you run 2 times SGD, you will have each time different realizations of the mini batches, which means that each time you will compute a gradient, it will be different. It will be a function of which mini batch you chose and what samples are in this mini batch. Okay, this is why it becomes stochastic. So each time you will compute, so okay, concretely, you take your samples. Let's say there are n points. Okay, and you convert that into mini batches. So here you have the samples. Okay, this is your whole data. And instead you will create mini batches, which are subsets. Okay, let me say X. Which notation can I use? How do they write? Let's say okay, K1, sorry, Ki. For I equal 1 to, I will call M the number of samples in the mini batch, and this for K that goes from 1 to the total number of samples divided by the number of samples in each mini batch. Okay. Sorry. So, what is your question? Sorry. Yeah, each batch has the same number of samples, which is M. Let's say M is 10 or 100, you know, a small number compared to the total number of samples. And usually what you do is you create the mini batches in a way that a sample appears only in one of them. Okay, you don't have repetitions. So concretely, it means that if you have a mini batch xk I yki, so k is the index of the mini batch, and ki means the indices of the samples inside this mini batch. Okay, it's a double index. You should, it's okay, so you're not too confused. Okay. Okay, and let's say you take the intersection with another mini batch, k prime I y k prime I, is empty. Okay, so they have no samples in common. Okay, sorry, these mini batch are sets of pairs. One sample is a pair of input and output. Okay, concretely, this just means you take all your samples, you permute randomly your samples, and then you take the first 10, then the next 10, then the next 10, then the next 10. And this is how you create your mini batches. Okay. Then the SGD rule is very simple. Okay. Again, you have an initial T0. Okay. And you loop over T. You compute again VT, which is the learning rate times the gradient with respect to the cost, and I will write cost cost MB for mini batch. Okay. What does it mean? The cost mini batch concretely it's a sum. Sorry. It's a sum for all pairs I equal 1 to M now of the costs evaluated on the points Y, K, I. Okay, and this is your estimator evaluated on X, K, I. Okay, where this index here, in reality, it also depends on K, on which mini batch you are choosing. Okay. And each time you do an iteration, you go to the next mini batch. Okay. If you want, here I can put a K equal K plus 1. Okay. So you loop over the mini batches like this. You apply the normal gradient descent algorithm, but each time that you do an update, you will evaluate the cost on a different mini batch, not on the whole data. Okay. So what you can do is that here, maybe you should put a line. I should put a line here at each actually, there should be a double loop because, okay, I will try it. I will write it more clearly. You first divide all your data into mini batches. Okay, so first you permute randomly your data. You divide into mini batches. You loop over all the mini batches. So you compute the gradient on the first mini batch, then second, then third, etc., etc. until you reach the last mini batch. Okay. And then what you need to do is to reshuffle the whole data, create again new mini batches, and restart. Okay, so running one time over the whole data, which means the whole all the mini batches, is what we call an epoch. So let me try to write the code correctly. It's not written there, but I will try. Let's see if I can improvise. Okay, so there should be 2 loops. There should be 2 loops. So I will do so for, let me call t equal 1 to t max. Okay. And then you have another sub loop here, which would be a for the mini batch index k going from 1 to we said the number of mini batches is what we called n over m. M is the number of samples inside a mini batch. M is small. Okay. This is the number of mini batches. Okay. Then you do the gradient descent step on this mini batch. Okay. Which concretely means that. Oops, what happens? Oh, no, it's okay. Okay, and that's it. And here, okay, sorry, here I should have a subroutine. Why is there is a bug? Okay, here there is a subroutine. I just write in words. Create a random set or create random mini batches. Okay, so you have 2 times indices. This is the index this is the index over the epochs. Okay, epochs index, and this is the index over the mini batches. Mini batch index. Okay, so at first epoch, you create a random, you create m random mini batches. Okay, so again, how to do, what is the simplest way? You take a random permutations of the data and you cut it into non-intersecting mini batches. Okay, and then for each of this mini batch, you compute the gradient rule. Okay, you compute the normal gradient descent. Then you go to the next mini batch, then to the next, then to the next. And once you run through all the mini batches, you did one epoch, you go back to creating a new random selection of mini batches, and you go again along all of them. You go through all of them, and so on and so forth. Okay, so you have 2 time scales. Okay, one epoch means that you went through all the data once, which means you went through all the mini batches. Okay, and you see that now this operation here, which is here concretely, is much less costly. Okay, because now you have a gradient to compute, but over 10 points maybe, not anymore 100,000 or 1 million. Okay, so these gradients here, you see, is a kind of noisy approximation of the true gradient. Here I forgot an index T. Okay, noisy in the sense that you are computing just the gradient over few samples. You're not exploiting all the data each time you compute a gradient, just few points. Okay, so this generates stochasticity, and what is interesting is that this stochasticity is not only a way to dramatically reduce the computational cost, but it also helps a lot the algorithm to find good minima, which means to find minima that are close to the global minimum. And actually, in machine learning, to find minima that have good generalization properties, such that the model that you learn is good at prediction. Okay, so people like to say that stochastic gradient descent, the noise induced by stochastic gradient descent, is kind of a self-regularization, in the sense that this addition of noise, okay, or this noise is an SGD, allows to prevent overfitting. Okay, because you see, due to this stochasticity, you are less sensitive to, to possible local minima that are just due to finite sampling, to the variance in the data or details of the data. Okay, due to the noise, you will follow the gradient. You will follow the trend, if you want. You will fluctuate around the trend that may lead to the actual global minimum. If you have a small local minimum that could block gradient descent, due to the stochasticity, maybe at some point you will find a mini batch such that the gradient actually becomes negative. You see that each time, what you should have in mind is that in stochastic gradient descent, the landscape becomes dynamic. It's not anymore only that the particle is moving in a fixed landscape. The landscape becomes dynamic, because you see that each time here you compute this gradient here, this function here is what defines the landscape, right? The landscape is defined by the cost. But because the cost now is stochastic, in the sense that each time you choose another mini batch, the cost function has a different shape, then you have moving particles in a fluctuating environment. You see? And these fluctuations actually help you, they kind of average out the randomness of the data itself. And so it allows the algorithm to really converge in the directions which are statistically present for all mini batches, which means really the information contained in the data. You see? So these fluctuations of the landscape itself help you, actually. It's not only computationally speaking, but it really helps you to find the proper minima. And by proper, we mean the ones with good generalization properties. And also the global minimum, okay? I told you we are trying to find here the argmin, so really the global minimum of this high dimensional cost function. But actually, I claim that it is not always good to find a global minimum, because global minimum may lead to overfitting. Okay, it may be you have a complicated function, and maybe you have a global minimum like this, and then somewhere you have a much wider minimum here, which is not the global one here, but which is wider. And actually, there are many theoretical evidences that this is the kind of minimum you should aim for. These are the ones that are robust to fluctuations, which means good at generalizations. They're wide, and this is connected to good generalization properties. While this global minimum here, maybe it's just due to pure fluctuation in the data, okay? You see that if you had a different data set, this typically would not be there, okay? And stochastic gradient descent is actually very good at finding such wide minima, okay? Because you see, if you optimize mini batches, typically very sharp minima like this, they disappear from one batch to the other, so we'll never settle there. While this kind of wide minima are often, the information about that is contained in most mini batches, so you will converge there. Okay, all that is very empirical, but yeah, this is what is going on. Noise helps you. Okay, and okay, this all that goes beyond my knowledge, but also keep in mind that the type of noise induced by SGD, the stochasticity of SGD, is not just a Gaussian additive noise. Okay, it has correlation, it has a structure which is much more complicated than just an adding noise to the gradient. Because you could tell me, okay, Jean, that's nice, but why don't you, if we forget the computational issue for a moment, we could also maybe just look at gradient descent here and add Gaussian noise, for example. Okay, which means that you compute the full gradient, but you decide to add a bit of noise, to add stochasticity. People do that, okay, and this is called the Langevin algorithm. And it may work and be useful, but the type of noise induced by SGD is not of this form. It has much more complex structure and correlations, okay? Okay, I think I'm already way above time. I'm sorry about that. I will stop there. Next time we will discuss momentum. So please have a look. So we will, if we continue our explanations in terms of particles moving in a complicated landscape, in physical terms, we will now add momentum, inertia. So not only you will follow noisy versions, noisy approximations of the gradient, but we will add mass to this particle or memory of the past trajectory, so that the particle tends to favor the trajectory that it was following in the past also. You keep a memory of what is going on, which in physical terms means that you have inertia. Okay, you have it is costly to do drastic change in the direction. This is called inertia in physics. Okay, so we'll add inertia in the dynamics, which helps when you are close to minima to actually converge, like a ball rolling. You know, this inertia will help you to settle somewhere. Okay, so we discuss that next time, and we do some experiments, and that will be it. And then we'll do logistic regression, and hopefully we will code. At the end, ultimately, what I want to do is that we code logistic regression, which means a baby neural network to classify images. Okay, and you will code by yourself SGD, the neural network, and we'll do the classification task from A to Z without calling any packages. Okay, so that you will have done one time in your life, because then you will not do it anymore. You will call Python. Okay, but at least you will know one time how it's done. Okay, all right. Sorry for the delay. So is there a question for the people online, or? All right. All right. So I see for the people online, I see you on Monday. Okay, we'll send a link again and we continue. All right. So enjoy your weekend. Ciao.
Thank you. You too.
No, you can.